You may remember that at the end of the last video we raised the question of whether dimensions of physical quantities can be used to do anything for us, and we also remarked there that yes, they can be used to check the correctness of equations in physics. And today we are going to see how in dimensional analysis and its applications. Let's start our discussion with these three expressions: 1 kilometer plus 1 second, 2 kilometer plus 3.1 kilometer, 23 second minus 15 second. You can clearly see that the first one does not make any sense. It is meaningless. It does not make sense to add distance and time. We do not get anything physically meaningful by doing so. But of course, these two expressions make sense. You can add two distances provided the units are the same. You can also subtract one time from another time provided the units are the same. And what do we do? What do we get when we do these calculations? Let me write the equations. These are expressions, but let's write the corresponding equations and see what we get. So we obviously get this. What else shall we get? 2 kilometer plus 3.1 kilometer is 5.1 kilometer, and 23 second minus 15 second is 8 second. But the observation here is that both the quantities involved here have the dimensions of length, and this side also has the dimension of length. So both sides, we would say that both sides have the same dimension. But plus is involved. Does that not affect the dimension on the left hand side? No, because you are adding the same quantities. Same quantities means, well, not exactly same quantities because the measurements are different, but quantities having the same dimension. So addition or subtraction do not change dimension. So although you are adding and two different quantities are involved, but because they have the same dimension, the dimension of this combined quantity is also that same. That is because unit is not changing. No, distance remains distance. And on the right hand side also, of course, the dimension is that of length. Here also the dimensions on both sides are that of time. So what do you see from these two equations? The conclusion here is that a correct equation should have the same dimension on both sides. And if addition and subtraction are involved, you have to check the dimensions of the individual quantities which are being added and subtracted. So if that matches, then we would say that the equation is dimensionally correct or dimensionally consistent or dimensionally homogeneous. Otherwise, it's inconsistent or non-homogeneous. So if you encounter an equation in physics, you can check if it is dimensionally correct by investigating whether the dimensions on both sides are equal, and that is your dimensional analysis. Note one more thing, that simply having the same dimension on both sides of an equation does not guarantee that it is actually physically correct. Let me give you one example. Say someone has done this calculation, someone is not in the right state of mind and did this. On this equation, if you apply that dimension thing on both sides, you get that yes, both the quantities on the left hand side have the dimension of length, and the quantity on the right hand side also has the dimension of length. So this equation is dimensionally consistent or homogeneous or correct, but obviously it's not correct. Similarly, here the mistake is mathematical, but elsewhere it may not be so easy to spot. Say you see one equation involving a few physical quantities, momentum, anything, okay, temperature, something. then you may not know if it is really physically correct, but it may turn out to be dimensionally correct. So if an equation passes the dimensional consistency test, then it's not guaranteed to be an actual physical equation. For that, you have to go to the theory from where this equation is derived, or you have to perform some experiment and see if it really is. I mean, if you are really getting in the experiment what the equation is predicting. Okay, but if an equation is dimensionally incorrect, dimensionally inconsistent, then you can immediately say that yes, it is false. There is no need for performing physical experiment, no need to go back to the theory to see if it is correct or not, because the dimensions are not matching on both sides, so it cannot possibly be true. Okay, so that is where dimensional analysis is used. Let me give you one example of that. Say this equation says someone was in a hurry and did the calculation wrongly, and the mistake is this. On this side you have the dimensions of velocity, but on that side you have the dimension of length. So this is a dimensionally inconsistent equation. So if that's the case, then obviously the equation is false. No need to check anything else. So you see that addition and subtraction do not affect dimensions. First of all, you can only have the same dimension in all the quantities, then only you can add or subtract. And the second thing is that the act of addition or subtraction keeps the dimension same. However, when multiplication and division are involved, then obviously you can involve quantities having different dimensions. For example, we have already seen this. Displacement has the dimension of length. Time, well, of course, it has the dimension of time. So these are different dimensions. Quantities having different dimensions. But you can divide one by another and you can have a physically meaningful another type of quantity which has another dimension. Okay, so multiplication and division can involve physical quantities having different dimensions. And for example, you can multiply mass and velocity to have momentum. They have different dimensions, but still you can multiply. So now next what we are going to see, next let us take one example and see how we can apply this method to that example to see if the equation is dimensionally consistent or not. Suppose a particle is moving along a straight line with uniform acceleration a, and say it started moving from the position x0 on the straight line with initial velocity v0. Then its position x at time t is given by this equation. X equals x0 plus v0 t plus 1/2 of acceleration times time square, at square. Is this equation dimensionally consistent? Let's check. So we calculate the dimensions of all the quantities involved here. The dimension of x is length. The dimension of x0 is also length. The dimension of v0 t is the dimension of v0 times the dimension of t. When multiplication and division are involved, you treat the quantities as if they are algebraic symbols, and you can calculate dimension like this. So if the quantities are multiplied, then you multiply the dimensions. And then what is the dimension of v0? Since v0 is velocity, initial velocity, so its dimension is Lt to the power minus 1. And the dimension of time is t. So then this t inverse and t cancel out and you are left with L. So yes, v0 t is the quantity which also has the dimension of length. and then we have 1 over 2 times at square. Its dimension is the dimension of 1 over 2 times dimension of acceleration times dimension of square of time. This is a pure number, it's a dimensionless quantity. You remember that thing, because this does not have any unit, and actually does not have any unit in terms of the 7 base units. In that sense, it's dimensionless. So we do not write anything here, but if you want, you can write L0, T0, those things you can write. Actually, that is what we have here, but because ultimately that is not going to affect anything, that's why we did not write it here. The dimension of acceleration is Lt to the power minus 2, that we already know, and the dimension of time square is T square. So these two things cancel out, and then here also we have L. So all the quantities involved here have the dimension of length. The left hand side has only one quantity, so the left hand side has dimension of length. The right hand side has three quantities, and addition is involved because addition does not change dimension. So the combined dimension of the right hand side is also length, and that's why this equation is dimensionally correct. That alone does not tell us that it's really correct. For that we have to go to the theory of motion along a straight line, and from there we have to see how this equation is arrived at. You may notice one thing, that actually the fact that all these quantities have the dimension of length really has nothing to do with this number 1 divided by 2. So if, say, someone changes this and makes it at square, obviously the equation has changed, but dimensionally it hasn't been affected. Still we have the dimension of length on both sides, but maybe this equation is not true, who knows. Maybe the original one is true, but maybe this one is true, the original one is false. That's why only dimensional consistency won't tell you if the equation is true. But if we had different dimensions on both sides, then you can say for sure the equation is false. Let us see another example. There was one heading before the previous equation. The previous equation comes under the heading checking the dimensional consistency or homogeneity of equations. But headings, of course, are not that important. The content, the actual content is what matters. And after that we have this example, 1.3. And the equation here is this: 1/2 of mv square equals mgh, where m is mass, v is velocity, g is acceleration due to gravity, and h is height. In what context these quantities are being considered, we are not going to go into that because that's not the purpose here. And you actually already know what the left hand side is. It's the kinetic energy of a moving object, and the right hand side is potential energy. We have to check if this equation is dimensionally consistent. So let's calculate the dimensions on both sides. And here addition and subtraction also are not involved, only multiplication and division. Division, well, if you consider this as division. So let's see. So we first calculate the dimension of the quantity on the left hand side of that equation, 1/2 mv square. So that equals this. This is dimensionless. Mass has dimension of mass, and v square, velocity, has dimension Lt to the power minus 1. Its square will have dimension L2 t to the power minus 2. So the combined dimension is ml square t to the power minus 2. And then we calculate the dimension of mgh. So that is this. Here m has the dimension of mass because it is mass. G is acceleration due to gravity, so it has the dimension of acceleration, L t to the power minus 2. And h is height, so it has the dimension of length. So this L and this L give us L square. And that way here also we get the same dimension, m L square t to the power minus 2. So yes, that given equation is dimensionally consistent. From this alone, we cannot of course say that it's actually true or correct. There are two more things here in this chapter that we will do in the next video on physics on this same day next week. So see you next week with that. Until then, this is me, Lucifer, from A Mathematical Group. Have a nice day.